Welcome back. This will be the second part, or part B, of a video lecture on section 3.6 from the text covering linear transformations. Now, in our first part, we covered linear transformations and special transformations in the plane. In this second video, we'll pick up where we left off, and we will look at new linear transformations from old, inverses of linear transformations, and finally, associativity. So let's begin with new linear transformations from old. Given the linear transformation t from Rn into Rm, we're going to let this symbol, t wrapped by a pair of square brackets, that symbol is going to denote the matrix associated with the transformation. Now, our next theorem says something very important about the composition of linear transformations. Let T be a mapping, a transformation from Rm into Rn, and let S be a transformation from Rn into Rp. And let's assume that those are both linear transformations. Now, our theorem 3.32 has two important conclusions. First, the composition of S with T is a map from Rm into Rp. That is a linear transformation. Second, the standard matrix associated with that composition, the standard matrix of S composed with T, is the product of the standard matrices associated with S and T. Now, let's go to the document camera to unpack and prove theorem 3.32. All right, welcome to the document camera. Let's look at the proof of theorem 3.32. And let's remember, in this theorem, T is a linear transformation from Rm to Rn. S is a linear transformation from Rn into Rp. And when I compose S and T, S composed with T, that's going to give me a transformation from Rm into Rp. Now, our first job is to show that S composed with T is in fact a linear transformation. And then we'll show that the matrix associated with S composed with T is just the product of the matrix associated with T times the matrix associated with S. So let's do this part first. And what we're going to do is take a linear combination of vectors in Rm. We'll begin with C1U1 plus C2U2, where U1 and U2 are coming from Rm. And what we want to do is apply the composition of S and T to that linear combination. Now, by the properties, or by the definition, if you will, of function composition, this is S of T of C1U1 plus C2U2. Now, here we're going to use the linearity, the fact that T is a linear transformation. I can think of this as S of C1 T applied to U1 plus C2 T applied to U2. All right, that's using the fact that T is a linear transformation. Now we'll use the fact that S is a linear transformation, and we'll write this as C1 S of T of U1 plus C2 S of T of U2. And now we'll just rewrite this using composition notation. So we can think of this as C1 S composed with T applied to U1 plus C2 S composed with T applied to U2. And if we step back and look at this, if we think of S composed with T now as a single transformation, we're showing that S composed with T applied to this linear combination is just a linear combination of S composed with T applied to U1 and S composed with T applied to U2 using exactly the same scalars. And that shows that S composed with T is a linear transformation. It satisfies that defining property. All right, our next task is to show that we can always calculate the matrix associated with S composed with T by simply multiplying the underlying matrices, the matrix associated with T and the matrix associated with S. Now let's do this by taking a vector x out of Rm. So let's let x be a vector in Rm. Okay. Now when we look at the action of S composed with T on that vector x, by the definition of function composition, this is the same thing as S applied to T of x. But by the definition of the matrix associated with this transformation T, we can always calculate T of x by matrix multiplication. We can think of that as the matrix T times the matrix X, where I think of this as a column. Okay, so I can always treat T of X as the matrix T times the vector or the matrix X. All right. Now, this is just another vector, and by the definition of the matrix associated with the transformation S, I can always think of this as S applied to that vector. I should say the matrix associated with S applied to that vector. And now by reassociation, I can think of this as S times T times that vector X. And what this is showing us is that S composed with T applied to X can be thought of as this matrix times that vector X. So this is the matrix associated with S composed with T. In other words, the matrix associated with S composed with T must be the matrix associated with S times the matrix associated with T. All right, and that brings our proof to a conclusion. So let's go back to the course notes. Now let's put theorem 3.32 to work for us. Let's create a reflection in the plane through the line y equals 3/4 x. So join me at the document camera to work out the details for this linear transformation. Welcome to the document camera. In our solution, we're going to let T stand for the transformation that takes a vector in the plane and reflects it through the line y equals 3/4 x. Now, I'm going to show you that T can be described as the composition of three elementary maps. And in order to describe these maps, I'm going to have to describe this angle theta here. So let theta be the angle between the positive x-axis and our line y equals 3/4 x. Okay, so here's our three elementary transformations. The first one is going to be a clockwise rotation of the plane through theta. I'm going to call that map rho of theta for a clockwise rotation through theta. The second map is going to be a reflection through the x-axis. So to take the plane and reflect it through the x-axis, I'll call that map or transformation M. And the last step, the last transformation is a counterclockwise rotation through the angle theta. And I'll call that map R sub theta. All right. So the claim is that T can be affected by first doing rho of theta and then composing that with a reflection and then composing that with another rotation. So we'll have a clockwise rotation, a reflection through the x-axis, and then a counterclockwise rotation. All right. Now, what the theorem that we just studied says is that if I want the matrix for T, all I have to do is find the matrix for rho, M, and R and multiply the matrices. All right, so our work is really reduced to this, right? We have to work out the matrix for rho of theta, we have to work out the matrix for M, and then we have to work out the matrix for R of theta, and then we simply have to do the matrix multiplication. All right, now let's work out the matrix for rho of theta first. Now we have a matrix representation for a counterclockwise rotation through an angle. And so one thing we can do is leverage that result and realize that a clockwise rotation through theta is equivalent to taking our regular counterclockwise rotation matrix and applying an angle of negative theta. All right, so in other words, a counterclockwise rotation of negative theta is equivalent to a clockwise rotation of theta. Now, we've got our rotation matrix. I'm just going to substitute negative theta in for theta everywhere, and it's going to look like this. we'll have cosine of negative theta, sine of negative theta, the negative of the sine of negative theta, and the cosine of negative theta. Now, let's use the fact that the cosine is an even function and the sine is an odd function. We can go in here and clean this up a little bit. The cosine of negative theta is just the cosine of theta. The sine of negative theta is the negative of the sine of theta. The negative of the sine of negative theta, by cancellation, is just the sine of theta. And the cosine of negative theta is just the cosine of theta. So here's a matrix that describes a clockwise rotation through the angle theta. Now we have enough information to work out the cosine and the sine for this angle theta. Let's take a look at a triangle that we can impose in this picture here. Because the slope is 3/4, we know, for instance, that if we go over 4, we'll go up 3. So we can look at a triangle that's got sides of length 4, 3, and a hypotenuse of 5. And so by looking at this triangle, for example, we can see that the cosine of theta is 4/5 or 0.8, and the sine of theta is equal to 3/5 or 0.6. So by substitution, we can see that our first matrix, the matrix for rho of theta, if you will, is going to have entries 0.8, 0.6, a negative 0.6, and 0.8. All right, and that's actually most of the work. This is, of the three, this is the one that's the most difficult to work out because it involved a couple of steps. All right, now we know how to get a reflection. This reflection map is quite simple. The matrix for that reflection map is going to be 1, 0, 0, negative 1. And then finally we have to get r of theta. Now that is just our typical counterclockwise rotation through the theta. And so this is going to look like cosine of theta, sine of theta, negative sine of theta, and cosine of theta. Now for this particular angle theta, we've worked out the cosines and the sines, and so we know that this is going to look like this: 0.8, negative 0.6, 0.6, and 0.8. Okay? Our last step now is just to bring all of these ingredients together and use our theorem that says the matrix for T is simply the product of the matrices for the underlying maps in our composition. So the matrix for T is going to be what I get when I multiply the matrices. So we'll have 0.8, negative 0.6, 0.6, 0.8. In the middle, we'll have this matrix, the reflection. And then on the far right here, we're going to have our matrix that involves, that corresponds to our clockwise rotation. So 0.8, 0.6, negative 0.6, and 0.8. And you can multiply all these matrices together. And our result is going to be the 2x2 matrix with entries 0.28, 0.96, 0.96, and negative 0.28. That's the result of doing the matrix multiplication. So this matrix will have the desired effect. This matrix will affect the reflection of a vector in the plane through this line y equals 3/4 x. So the main takeaway here is that we can build other transformations in the plane using some elementary transformations, and the idea that composing these transformations at the level of matrices involves matrix multiplication. So that's the big takeaway from this problem. All right, let's head back to the class notes and continue. Our next topic is inverses of linear transformations. Now let S and T be linear transformations from Rn to Rn. Then S and T are inverse transformations, provided that S composed with T is the identity transformation, and T composed with S is the identity transformation. Now this is just a fancy way of saying that the transformations S and T undo each other. So for example, if the transformation T takes the vector x to the vector y, then the transformation S takes the vector y back to the vector x. So that's what it means to say S composed with T is the identity transformation. X goes to y, back to x. Now likewise, if S takes the vector y to x, then T takes that vector x back to y. And that's what it means to say that T composed with S is the identity transformation. T and S have the property that they undo the work of each other. Our next theorem says something very important about the standard matrix associated with an inverse transformation. Let T be a transformation from Rn to Rn. Let it be an invertible linear transformation. Then its standard matrix, bracket T, is an invertible matrix, and the standard matrix associated with T inverse is the inverse of the standard matrix associated with T. Now let's put theorem 3.33 to work. In this problem, I want to find the inverse of the rotation transformation R sub theta, and I want to do this in two different ways. One is algebraically using theorem 3.33, and the other way is to think about it geometrically. So join me at the document camera to look at two different perspectives on finding the inverse of this rotation transformation. All right, welcome to the document camera. In this problem, we're going to find the inverse of this rotation transformation, and we're going to do it in two different ways. One, we're going to think about it purely as an algebraic problem. We have the matrix for this rotation, and so that's going to amount to finding the inverse of this matrix. And our second way is going to be just to think about this transformation geometrically and work out its inverse, just thinking about the rotation transformation geometrically. All right, let's do the algebraic solution first. So what we have to do is we have to take this 2 by 2 matrix and find its inverse. Now we know for a 2 by 2 matrix that that's actually pretty easy to do. First thing we'd have to do is calculate the determinant of this matrix. So the determinant of R of theta is going to be cosine squared minus, we'll have sine of theta times the negative of sine theta. That's the negative of sine squared. So because of this negative sign, that will become plus sine squared. And we know that cosine squared plus sine squared equals 1. All right, so the inverse of this matrix is going to be 1 over 1. 1 over the determinant, 1 over 1. Now I take the two entries in these diagonal positions and I switch them. In this case, since they're both equal to cosine of theta, that will have no effect. And then I change the signs in these off-diagonal positions. So that's going to put a sine of theta here and a negative of sine of theta in this position. So there's the inverse matrix of R of theta, and that is going to therefore be the inverse transform. That will correspond to the matrix of the inverse transformation for this rotation matrix. Okay, now that was done purely on algebraic grounds. We have the matrix for R of theta. We can find its inverse. Now, let's think about the problem geometrically. We know that the transformation R of theta is going to take a vector in the plane, and it's going to rotate it counterclockwise through theta. And so if we want to undo that, we know we're going to have to rotate clockwise through theta. So the inverse of this transformation is going to be a clockwise rotation through theta. And as in our previous problem, we know that that's the same as a counterclockwise rotation through an angle of negative theta. Okay? So the inverse, just on purely geometric grounds, the inverse transformation for r of theta should be a counterclockwise rotation through negative theta. Now, we've been through this exercise once before, but let's just take a look at the math again. This is going to be effectively plugging negative theta in everywhere we see theta in this rotation matrix above. So we'll have the cosine of negative theta minus the sine of negative theta, the sine of negative theta, and the cosine of negative theta. And as before, using the even and odd properties of the cosine and the sine function respectively, this is going to reduce to cosine theta, sine theta, the negative of the sine of theta, and the cosine of theta. And you can see that in both cases we get exactly the same matrix. So we can think about it as a geometric problem, or we can think about it as a purely algebraic problem. No matter how we think about it, we can work out the matrix for the inverse transformation, and we can see that the result is the same in both cases. All right, let's head back to the class notes. Let V be the vector with components 3/5 and 4/5. In a previous problem, we found the matrix associated with the transformation. T of u is the projection of the vector u onto the vector v. Now, in this problem, we want to show that T is not invertible, and we'll look at this from both the algebraic and the geometric perspectives. So join me at the document camera for an analysis of this problem. All right, welcome to the document camera. In this problem, we've got a transformation T, which takes a vector in the plane and projects it onto the vector v, which has components 3/5 and 4/5. Now, we worked with this example in part A of the lecture, a video lecture on section 3.6. And in that video lecture, we worked out all of the entries of the matrix associated with this transformation T. Now, what we want to show is that T is not invertible. And that's pretty simple because we know that the inverse of this transformation T would be related to the inverse of this matrix. And so we just simply have to show that this is not an invertible matrix. And for a 2x2 matrix, we can do that by looking at its determinants. So if we check the determinant of T, it's going to be 0.36 times 0.64 minus 0.48 times 0.48, so minus 0.48 squared. And when you work that out, you get 0. And that shows us that T is not invertible. And that basically is all we would have to do to show that the T has no inverse, is that its matrix is not invertible. Now, let's look at this, though, from the perspective of our fundamental theorem on invertible matrices and see if we can gain another perspective on why this transformation is not invertible. Now, remember, this transformation is doing a projection, right? It's projecting vectors in the plane onto this vector v. Now, what I've drawn here is the line that's perpendicular to the line that's given by the direction vector v. So we have within the plane a line that's perpendicular to the line that's determined by that vector v. In particular, one vector whose tip is on this line would be the vector with components, let's say, 4 and -3. We can easily check that this vector is orthogonal to the vector v, okay? We can just take the dot product and see that. In particular, we can see that this vector, through this transformation T, is going to be sent to the 0 vector. In particular, that shows us that the null space of T is not trivial, right? It doesn't consist just of the 0 vector. There's a vector v here, for instance, that through the transformation T is getting sent to the 0 vector. So the null space of this transformation is not the 0 vector. And we know from our fundamental theorem on invertible matrices that if T were invertible, the null space of T would be the zero vector. And since the null space of T is not the zero vector, T is not invertible. So we can see that this transformation is not invertible on these algebraic grounds. We can see that the matrix is not invertible, but we can also understand it geometrically. We have a whole dimension in the plane that's being squashed to the zero vector, being sent to the zero vector. And by our fundamental theorem on invertible matrices, since that null space is not trivial, the transformation is not invertible. Okay, let's head back to the class notes and continue. Our final topic is associativity. And I want to work one problem with you regarding associativity. Let's first recall Theorem 3.3. Now in Theorem 3.3, we gave 5 important properties of matrix multiplication. And property A addresses the all-important property of associativity. Now, what I want to do is show you how we can use linear transformations to provide a fairly clean proof of matrix associativity. So join me at the document camera for the proof of Theorem 3.3a via linear transformations. All right, welcome back to the document camera. We're going to work out the solution to this problem, and we're going to do this in 2 separate steps. The first thing I'm going to do is remind you of a fact about functions and function composition, that function composition is associative. So we'll show that f of g of h is the same thing as f of g of h, all right? And then we'll show how we can use this result to prove that matrix multiplication is associative, because we'll be able to apply this result to the transformations that are derived from matrices, all right? So we'll get there. Well, that'll be part of step 2. Let's first of all talk about this result. So if I ever want to show that 2 functions are equal, I just have to show that they operate in exactly the same way on every input variable, right? So that for every single input variable, they produce the same output. So let's think about what happens when I apply f of g of h to an input variable x. Okay, so I've got a left function and a right function being composed and operating on the variable x. And so the rules for function composition are take the right function, apply it to x, and then wrap that with the function f. So this is going to look like f applied to g of h applied to x. Now using that function composition rule one more time, I can see that this is going to be f of g of h of x. Okay, so that's what happens when I take this function on the left and evaluate it at an input variable x. Now let's do the same thing on the right. If I start with f of g of h of x, I'm going to take my function here on the left, f of g, and I'm going to apply it to h of x. But again, I've got a function composition here, so this will be f of g applied to this variable h of x. So f of g applied to h of x. And so we can see that for every input variable x, these 2 functions always evaluate to the same output, right? So these 2 functions are equal to each other. So that's just a reminder, right, that function composition is associative. Now, let's see how we can leverage that, all right? Now, we're looking at a product of 3 matrices, A, B, and C. So let's think about the matrix A times B times C. And let's think about the transformation that's associated with that matrix. So let's think of T, the transformation derived from the matrix product A times B times C. Now we know that because this is a product of 2 matrices, I'm going to call one matrix A and the other one B times C. So this is a product of 2 matrices. We know that the transformation that's associated with the product of these 2 matrices is a composition of 2 transformations. So this will be the transformation derived from A composed with the transformation derived from BC. Okay? But this once again is a product of 2 matrices. This is B times C. And so this transformation can be thought of as itself another composition, the transformation derived from B and the transformation derived from C. Okay? So the transformation of the matrix A times B times C can be thought of as a composition of three transformations where I'm keeping these parentheses here. I'm thinking of T composed with TB composed with TC composed with TA. And now let's work out the transformation associated with A times B times C. This is a product of two matrices, one called AB and the other called C. So this must come from the transformation associated with A times B composed with the transformation that comes from C. But once again, this is a product of two matrices. And so this can be rendered as the transformation associated with A composed with the transformation associated with B composed with the transformation associated with C. Now we know from basic function composition that these are in fact the same, right? Here's where we kind of see something that's now finally helpful, right? We can see that through function composition that these are identical. These are the same, right? That's just this general law. So since these are equal to each other, these two transformations must be equal to each other. And since these two transformations are equal to each other, the matrices that are associated with these two transformations must be equal to each other. So in fact, A times BC must be the same thing as AB times C. In other words, the associativity of matrix multiplication it can be, in some sense, discovered through the associativity of function composition. All right, thinking of the transformations that come from matrices allows us to kind of show in a nice, clean way that matrix multiplication, in fact, is associative. All right, now that brings a close to section 3.6, and I hope you've enjoyed that. We're going to go into section 3.7, and I will see you when we enter section 3.7 for another video lecture. Until then, take care. Bye-bye.